In this video, we are going to discuss independence for multivariate normal. So the basic idea is this: suppose I have a random vector x which has multivariate normal with whatever parameters, and if I expand x, here is one component xi and another component xj. I am interested in knowing when they are independent. Now, one condition we know: if xi and xj are independent, then we must have covariance of xi and xj is also equal to 0, and this covariance of xi xj is nothing but the ijth entry of this covariance matrix. So if they are independent, then this covariance will be equal to 0. Now we know in general for any two random variables xi and xj, covariance equal to 0. That does not imply that they will be independent, but in case of multivariate normal, it is actually true. To prove that converse, we need to know about a property of multivariate characteristic function. Suppose that we have one random vector x with multivariate characteristic function given by xi x t. So whatever is the length of x is same as the length of the t vector. Now imagine that this x is partitioned into two parts, y and z. Say the first m components are in y and the next n components are in z. So totally there were m plus n components in x. So there were the same number of components in t, m plus n. Now I can split all those components here also into two parts and write this function as function of u and v. So u and v are the two parts of t. I have partitioned t exactly in the same way as I have partitioned x. So now I have got three random vectors in my hand: x, y and z. Just as x has a characteristic function, similarly y and z also have their own characteristic functions, which I denote by xi subscript y. I use the dummy variable u, and here z, the dummy variable, is v. Now the theorem is that y and z, these two parts of x, are independent if and only if the characteristic function also factorizes. Xi x can be written as a product of xi y and xi z. Now the proof is extremely simple because these are nothing but expectations. So if they are independent, expectation will factorize. Simple. And why does it hold in the opposite direction? It holds in the opposite direction because characteristic function characterizes. So once the characteristic function matches, it must have the same distribution. From this we get the other end. Now let us apply it to our multivariate normal distribution. In the theorem that we are going to discuss, we again start with some random vector x having multi-normal distribution. Now we are going to partition x into two parts, x1 and x2. Now accordingly we shall partition these things also in appropriate parts, mu1, mu2. So there are as many components here as there are here, similarly here, and we shall partition capital sigma as sigma 11, sigma 12, sigma 21, which is actually sigma 12 transpose because it's symmetric, and sigma 22. Again, if there are 5 components in x1, this is 5 by 5. And similarly, if this is 6 components here, 6 by 6, and these are appropriate sizes such that you get this rectangular structure. So this is what we are starting with. Now we are going to investigate whether these two components are independent or not. Then these two components are independent if and only if this off diagonal block sigma 1, 2 is the zero matrix. Of course, that means this is also the zero matrix. Now one side is straightforward because if they are independent, then all their covariances will be 0, which means this will be 0. So that side is just true. We do not need any normality assumption for that. It is this side which requires the normality assumption. Here we shall remind ourselves about the characteristic function of multivariate normal. I have just added it as a note over here. Now what we are going to do is we are going to split this t vector, which is as long as this vector, into two parts, t1 and t2. Then let us see what happens to these two parts. This part, t prime mu, can be written as t1 prime, t2 prime. They are all now lying down as row vectors, and mu1, mu2. So by rule of partition matrix multiplication, I know that these things can be treated as ordinary numbers, and the product will be this times this plus this times this. So this term nicely splits up into two terms. Similarly, this term t prime sigma t, when I expand it, will look like this. This is t prime, the big sigma matrix, and again t. Now if you do the multiplication, you have to actually carry out the multiplication, and you will see that it will turn out to be t1 prime sigma 1 1 t1. It will come from this, t2 prime sigma 2 2 t2, this. Now there will be two terms which will be just transposes of each other, but since these things are all one by one, so transposes are same as itself, so it is just two times. I have written only this as the representative thing, t1 prime sigma 1 to t2, which means I had one term like this, the other was t2 prime sigma 1 to prime t1, which is actually transpose of this and equal to this. So that is why I am writing it plus 2. So it is a plus b whole square kind of idea. Now remember, our condition was that sigma 1 2 happens to be 0. So this part was really not there. I mean, there were big zeros. So this is also not present. So again you find, just like this, it's split up into two parts, one for t1, another for t2. Here also I get t1 and t2. This was the part which involved both t1 and t2. Fortunately, that is killed. So now I can write down this characteristic function for the whole x as, first I am writing down all the t1 things. This from this and this from this. Then I will collect all the t2 things. So I get this entire thing. Now it is e to the power, then the entire story. So of course by property of e, I can say it is e to the power this times e to the power that, which immediately shows that the characteristic function of the top part x1 times the characteristic function of the bottom part x2. So since the characteristic functions are multiplied together, so we can conclude that x1 and x2 must be independent. Here is an important corollary where we start with x, a multivariate normal, but not a general thing. I need identity for this thing to work. Then I take two fixed matrices, P cross n and Q cross n. Notice that this is n-dimensional. So the number of columns must be n. I do not care what the number of rows are. They are just any P and Q, need not be same. Such that A, B transpose is 0. A, B transpose is a product that you can form because both of them have n. So this is the 0 matrix. Then AX and BX, both these things can be formed because I have number of columns n. So these two random vectors must be independent. So this is very useful because independence is actually a stochastic condition and this is a linear algebraic condition. So this allows us to use linear algebra to control probability in case of multivariate normal. And if these things are just like vectors, in that case this is essentially saying A and B are orthogonal vectors. So orthogonality in case of linear algebra translates to independence, stochastic independence in case of probability for multivariate normal. The proof is quite easy. Just stack one on top of the other to create a long random vector. We are going to show that it has got a multivariate normal distribution with the appropriate off-diagonal block equal to 0. Now you can factor out x to write like this. A fits perfectly over B because both of them have the same number of columns. And we already know how to find out distribution when I pre-multiply by a matrix. It is normal with A and B. I should not say N here. It is P plus Q. And then whatever is the mean, I do not care. So I've just written star, and then this is this matrix times the identity matrix, which I'm not writing. Then A transpose, B transpose. So just do the multiplication and you will get this matrix. Now my condition is A, B transpose is 0, which means this is 0. And of course that also forces this to be 0. It is just transpose of each other. So the off-diagonal block vanishes, and immediately from that theorem we know that these two things must be independent. And actually this is also an if and only if result. If these two things are independent, this block must vanish, so this must be equal to 0. But it is this direction which is the most useful. Now in this very important theorem, we again start with a multivariate normal vector where the dispersion matrix is identity. I do not care about what the mean is, just any mu. Now, entire story is happening inside Rn. I take two mutually orthogonal subspaces. When I write less than or equal to here, I mean subspaces S and T inside Rn. They are mutually orthogonal. So something like AC is the xy plane in R3 and T is the z axis in R3. So I have got two such things. Now what I do is this x is a vector, it's a random vector in Rn. So I can project it orthogonally on S. I can also project it orthogonally on T. Let y and z be the orthogonal projections of x on S and T. Just as an example, if you are working in R3 and this is your x1, x2, x3 and S is your xy plane, then the projection of that onto the xy plane will be x1, x2, 0. Remember, it is not just x1, x2, it has to be inside Rn. So this is also of the same dimension. Similarly, the projection along the z-axis will be 0, 0, x3. So this is my y vector, this is my z vector. In this case, I can easily see that these are independent because I have chosen them so very nicely that x1, x2 is in one place, x3 is in another place, and because the variance matrix is I, so they are all independent, so clearly they are independent. But had I chosen these planes in a slightly oblique way, all of them will involve x1, x2, x3, but even then, y and z must be independent. And the proof is quite straightforward. Just consider PS and PT to be the orthogonal projector operators on S and T. Now this may sound like a very complicated thing. So this is a matrix, this is another matrix, they are both of order n cross n, and you are obtaining y from x as PS times x. So whenever you multiply any vector with PS from the left, you get the projection. Similarly for z. Now I hope you know that for any orthogonal projection operation, PS and PT should be symmetric matrices. In fact, they should be symmetric and idempotent. I do not care about the idempotence here. All that I need is that they must be symmetric matrices. I am to show that they are independent. Now I already know from the last theorem, all that I have to show is PS PT transpose equals 0. Now I said that S and T are mutually orthogonal. So if you try to project something on T and then you try to project that on S, you will get only the 0 thing. Because once you project something on T, you get something inside T. And now trying to project anything inside T onto S will of course give 0 because they are already mutually orthogonal. So we have PS times PT equal to 0, but since it is a symmetric matrix, I might as well put a transpose. And that is exactly the condition that we had in the last theorem. A, B transpose equals 0 in that case AX and BX are independent, so we get this independence. In this exercise, we are drawing a picture of Rn, so just trying to visualize it as R3. I give you a subspace, which I am showing as a plane. This is my origin. I give you a random vector there, which is distribution, normal, in dimension, any mean vector mu, but the covariance matrix is identity, which means all the components are independent and they have got variances equal to 1. Now this random vector I am going to project orthogonally onto this space. So I get this projection, which I will call Y. Then I will consider this part, which is sometimes called the rejection, which is given by X minus Y. Your job is to show that these two random vectors are actually independent. So whenever you have got things that are orthogonal, they also give rise to independent random vectors when you are working with multivariate normal with something like I in the covariance matrix.